2,000 times during World War II, torpedoes found their targets in enemy vessels as the submarine fleet of the United States Navy established a mark unequaled in the history of naval warfare. The American submarine, which saw action in World War II, is as superior to our Navy's first practical submarine as the battleship Missouri is superior to her famous ancestor, the Constitution. Our first carrier, the Langley, which was a major achievement only 30 years ago, was just a crude forerunner of today's attack carrier with her brood of jet fighter planes. Back of each and all of these advances in our Navy's striking forces, there is a story of cooperation. For the men who sail the seven seas have long found powerful allies in those who sail the eighth sea, the vast and never fully charted ocean of scientific research. The atom bomb, spreading its mushroom cloud over Bikini Atoll in 1946, gave scientists and fighting men the opportunity to learn about the most destructive force yet devised by man and its effect on naval strategy of the future. But a bomb is atomic energy uncontrolled after its release, and men of science knew that the same energy kept under control might serve the Navy in a vastly different way. The means of obtaining that control was the reactor pile, the furnace of atomic energy. Here, the rare elements which produce nuclear fission in chain reaction, uranium-235 or plutonium, strategically placed, will release tremendous energy in the form of heat. In fact, at work in a reactor, a single pound of U-235 will provide as much heat energy as 2.5 million pounds of coal, or nearly 250,000 gallons of diesel fuel oil. And what is more, oil to burn requires oxygen. So does coal. But in the process of nuclear fission, no oxygen is required. To the men of the Navy, the new power source had limitless possibilities. None more immediately useful, perhaps, than in a submarine. A conventional sub using diesel-electric power attains its maximum range and speed on the surface. Later models, which use a snorkel or breathing tube to supply air for the diesels, achieve comparable range and speed just below the surface. But a fully submerged sub, despite tremendous improvements in batteries, which must then supply its power source, still can't maintain the speed or equal the range of either the snorkel sub or the surface sub. What's more, a sub on the surface is a comparatively easy target for the powerful electronic eyes and ears of an enemy. A snorkel sub is only relatively safer, while a fully submerged sub is safest of all from detection. But since it must surface eventually to recharge batteries, a patient enemy may still find his target. On the other hand, a submarine using atomic power with an air supply for crew could run submerged for weeks if necessary. As to speed and range, it was evident that an atomic sub should be able to cross the broadest ocean fully submerged faster than many ocean liners, and in the process use less than a pound of atomic fuel. The principle was clear. Let a nuclear reactor supply heat. Transfer that heat to boilers where water becomes steam to turn turbines, and let the turbines, through reduction gears, turn the propellers to drive the ship faster and farther than ever before. In theory, then, the atomic submarine was sound, but the problems involved in building one were staggering. The reactor itself. Of what material could it be built that would permit chain reaction while operating at the many different angles of submarine action and yet be able to survive combat shocks? How to transfer the heat from reactor to boiler? What liquid could withstand the great changes of temperature and still not act as a damper of the atomic fires? The pumping system. How to force the hot liquid from the reactor into the boiler and back to the reactor? Shielding. What substance would be light enough yet provide sure protection to the crew from the deadly rays nuclear fission produces? And finally, how to reduce the overall size of this normally bulky, complicated machinery and make room for it within a submarine, already the most compactly designed warship afloat. To answer these and the literally thousands of other questions involved, the Navy and the AEC authorized 2 separate submarine projects. Under these parallel projects, divergent but equally promising avenues of engineering and design were explored independently. Thus, the stage was set for the world's first atomic submarines, the Nautilus and the Seawolf. Much of the work on the atomic power plant for the Nautilus was carried out at the National Reactor Test Center near Arco, Idaho. Here in the empty desert wasteland, a full-size duplicate of the Nautilus engine was constructed and tested. In January 1954, the hull of the London yard of General Dynamic Company's Electric Boat Division, the organization charged with hull construction for both atomic subs. Meanwhile, development of the parallel Seawolf project has gone forward for many months, principally in Schenectady, New York, under the direction of the distinguished staff of General Electric scientists and engineers at CAPL, the Knowles Atomic Power Laboratory. Within these walls, under conditions of strict security, literally hundreds of highly trained scientists have been working with formulas that would have been meaningless a score of years ago, using techniques and, in many cases, tools which were inconceivable before the achievement of nuclear fission. This control room may bear little physical resemblance to the engine room of the finished Seawolf, yet behind its concrete walls is a full-sized reactor of the type which will drive that sub. And here, this has happened thousands of times. The chain reaction of nuclear fission has been started and stopped in the course of innumerable tests to determine the material and design of the Seawolf's atomic engine. In the Radioactive Materials Handling Laboratory, much new and necessary knowledge has been achieved in the handling of substances made hot with radioactivity. Mechanical hands daily perform tasks no human being could do directly and live. A section of metal designed for use in a vital part of the submarine engine has been made highly radioactive and is tested in a concrete-lined vault, where the eyes and hands performing the operation are a dozen feet away. The test determines how much radiation this machine part has absorbed and with what effect. Hundreds of other tests have determined how to prevent any structural failures that might have endangered the underseas operation of the finished sub. In every section of the Atomic Power Lab, all its workers, from the senior craftsmen in the machine shop adapting old skills to new needs, to the youngest graduates from the nation's leading technical colleges, on to the top-ranking nuclear scientists, engineers, and management, all have been working with the Navy and AEC toward a single goal: the design and construction of an atomic engine that is at once efficient, tremendously powerful, and safe. To this end of ultimate safety, extensive land-based tests were planned for the Seawolf's engines before their installation in the actual ship. In a peaceful valley far from the sea near Schenectady, the structure for the tests was built, a steel sphere 10 times larger than man has ever built before. To form the giant ball, more than 600 plates of inch-thick steel, perfectly preformed, had to be fitted with absolute precision. An elaborate X-ray system checked the perfect seal of every inch of the thousands of feet of welding involved. While CAPL scientists were sure that tests conducted within the sphere would involve no leakage of radioactive gases, the steel sphere structure has provided an added precaution, a kind of super safety valve. And even as the sphere was being built, a full-scale operating model of the engine and reactor room sections of the Seawolf was under construction. As both sphere and hull were completed, there came the important day towards which so many workers of so many crafts had worked so long. What might be called a scientific launching into a scientific sea, as the hull section was moved into the sphere and operational tests were begun. While reasons of national security must conceal details of the tests within that sphere, one thing is certain. Much will be learned here of the workings of atomic engines, not only for submarines, but for many peacetime uses as well. For passenger and merchant ships, for land transportation, for electric power plants, even perhaps for the huge airplanes of the future. Meanwhile, the atomic submarines progress from drawing board to the reality of ships at sea, newest bulwarks of our national defense, powerful symbols of continuing cooperation between our scientists, our engineers, and our men of the sea, working together in atomic engineering. As in every phase of defense operations, they will continue to increase the striking force of the most powerful Navy in the world. Torpedoes found their targets in enemy vessels as the submarine fleet of the United States Navy established a mark unequaled in the history of naval warfare. The American submarine, which saw action in World War II, is as superior to our Navy's first practical submarine as the battleship Missouri is superior to her famous ancestor, the Constitution. Who sail the eighth sea, the vast and never fully charted ocean of scientific research. The atom bomb, spreading its mushroom cloud over Bikini Atoll in 1946, gave scientists and fighting men the opportunity to learn about the most destructive force yet devised by man. Our first carrier, the Langley, which was a major achievement only 30 years ago, was just a crude forerunner of today's attack carrier with her brood of jet fighter planes. Back of each and all of these advances in our Navy's striking forces, there is a story of cooperation. For the men who sail the seven seas have long found powerful allies. More than 2,000 times during World War II,